Swayam Prabha. Digital India. Educated India.
So we already derived for example, the relationship between the time on O prime's clock, that is an observer sitting at x prime is equal to 0, as they go on moving to the right, what would happen to their clock compared to the time shown on O's clock. Okay, that is the time shown on O's clock, which is initially at t is equal to 0. So we had showed that t is equal to 1 over square root of 1 minus v squared by c squared t prime, which we can write as so this is the time on the moving clock. This is the time on the ground clock. Okay. And this is moving clock moving with a particular observer on the train. So the way to think about this is, imagine that O prime is moving to the right, and now as they're moving to the right, as they pass these different friends, the friends look in and see what time O prime's clock shows them, and they report that value of the time, which is t prime over here. Okay, and since all the ground observers have synchronized clocks, they can tell you the time at which they passed O prime, and that would also be the value on O's clock as well. Okay, and that would be the time t. So this would be the time that had ticked on O prime's clock. This would be the time that has ticked on any of the ground observers' clock, since they're all synchronized. But we can say in particular on O's clock. And this factor here is just gamma, or our boost factor. Okay? So what this tells us is t prime is equal to t divided by gamma. Okay, and we saw that in the or for speeds much less than the speed of light, gamma is just close to 1, and in that limit t prime would be t. Okay, that is, you recover the ideas of Galilean relativity, where all clocks just appear to tick at the same rate. However, what you can see is, now if I ask about a time interval as seen by the ground observer, which is some fixed value of t, would yield a value of t prime which is smaller. Okay, so a fixed time interval on the ground would result in t prime which is smaller by a factor of 1 over gamma. Now if you remember what gamma looks like, gamma as a function of v, okay, as v gets close to the speed of light, okay, it just shoots up rapidly. Okay, it starts from 1 and shoots up rapidly. So what this tells us is that as speeds get close to the speed of light, okay, the time interval that passes on the train appears to be smaller and smaller compared to the time interval that has passed on the ground. Okay, so in other words, moving clocks appear to tick more slowly than clocks on the ground. Okay, This same relationship between the time intervals, let's call this delta t prime, and let's call this delta t. This same relationship between the elapsed time intervals should be true for any observer on the train. So if I take any clock and ask on the train and ask how much time has elapsed on this clock after a time delta t has elapsed on the ground, that moving clock would appear to tick slower. Okay, and this relationship must be true because no observer on the train is special, right? So all their clocks must appear to tick at exactly the same rate relative to clocks on the ground. Okay, so the clocks on the train appear to have a phase offset relative to each other, and they all appear to tick in sync relative to the clocks on the ground, but they tick at a slower rate than the clocks on the ground. And let's discuss one more consequence of the special relativity transformations. Let's consider an observer on the train S prime, and let's suppose that this observer on the train S prime has a rod with a length of 1 meter placed on the train. Now, when they say that the length of this rod is 1 meter, what that means is that they're locating the endpoints of the rod at the same instant of time as measured by the synchronized clocks on the train. That is, they locate one end of the rod, which is, let's say, at XA prime, and they locate the other end of the rod, which is at XB prime, but they locate both ends of these rods at the same instant of time. T prime is 0, let's say, and T prime is 0, according to their synchronized clocks. So in general, let's suppose that this length is L, and therefore XB prime minus XA prime is L. All right. Now let's ask, what is the length of this rod as seen by the ground observers? Okay, so the length as seen on the train, actually let's call this L naught. Okay, this is what is called, L naught is the rest frame length. This is the length of the rod as measured in the frame in which this rod is at rest. But now we want to know, in the frame S, okay, where this rod appears to be moving to the right, this rod is on a train, what is the length as measured by observers on the ground? Now, in Galilean relativity, we would say that this length has to be the same. However, the key point is, since time is relative in special relativity, you have to take into account the fact that the ground observer will measure the endpoints of this rod at different instants of time as seen by the train observer. So what would be a simultaneous measurement to the ground observer of the endpoints of this rod would actually be different instants of time as measured by the train observer. Now, using our dictionary of special relativity, we know that the coordinate position of the rod, of one coordinate, as measured in the frame S prime, is related to the coordinate position as measured by the ground observer, we'll call that XA, through this relationship. And similarly, the second position, XB prime, minus V times T. And the key point is that these instants of time at which we are trying to locate the coordinates of this rod, those instants of time would have to be the same instance of time when trying to measure the rod, the rod's length as seen by the ground observer. Okay, and since simultaneity is relative, the simultaneous measurement of these endpoints of the rod by the ground observer is not a simultaneous measurement as seen by the train observer. So relative to the train observer, the ground observer is moving to the left, and they are actually, as seen by the train observer, the ground observer is actually not inferring the length correctly because they are using different instants of time to measure the location of the endpoints of the rod. Okay, so if we now try to measure the endpoints of the rod at the same instant of time as measured by the ground frame observer, then they would say that these two times t are the same, and the length of the rod would just be given by xb minus xa. Okay, so we can work out what xb minus xa is by just subtracting these two equations from each other. So that would give us xb minus xa times 1 over square root of 1 minus v squared by c squared would be the same as xb prime minus xa prime. Or in other words, we could say that the length as measured by the ground observer, who is moving with respect to the rod, would be equal to the length of the rod in its rest frame, that is in the train, multiplied or divided by gamma. Okay, where this quantity 1 over 1 minus v squared by c squared is gamma. So this quantity L is the length of the rod measured by an observer or a frame, or measured in a frame moving with respect to the rod, and L naught is the length of the rod in its rest frame. And as we've seen before, for v much less than c, gamma is 1. This boost factor is 1, and L is the same as L naught. Okay, so that's what we expect in Galilean relativity, that the length of the rod does not change. But in special relativity, we see that as the speed v gets close to the speed of light, this boost factor gamma becomes very large, and the length of the rod that we measure in a moving reference frame is much less than the length of the rod in its rest frame. In other words, the rod appears to have shrunk or contracted in length. Okay, so we call this phenomenon length contraction. And we would say that the rod appears to be smaller as seen by the ground observer, or observer moving with respect to the rod. So, to summarize, we've seen three interesting observational consequences of special relativity. One is that the moving clocks appear to have a phase offset, and as you go along the direction of relative motion, these clocks appear to be further and further behind. And as you go opposite the direction of relative motion, these clocks appear to be further and further ahead. But all these clocks appear to tick at the same rate. However, the moving clocks all appear to tick at a slower rate than clocks on the ground. This phenomena is called time dilation. Or basically it's a way to say that time appears to be ticking slower, or things take longer as seen by the train observer. And finally, the last consequence that we saw is that moving rods or moving objects of fixed length appear to be shorter, smaller, as seen by the ground observer. Okay, so if they have a particular length in their rest frame, according to an observer who sees them in motion, they will appear to be shorter. This phenomena is called length contraction. So all of these phenomena start to become more and more important as we get to speeds which are closer to the speed of light. Okay? In the limit that the speed is small compared to the speed of light, these effects become more and more difficult to detect. And now, given that time and distances are both relative, it perhaps is not surprising that it can be possible now for different observers to perceive the speed of light to be exactly the same, no matter how fast they are moving relative to each other.